So good evening, everyone. This is GIS3043C, and this is lecture number 2, Introduction to GIS. All right, let's start with a definition of what is GIS. So the one I'm going to give you here is, definitions have changed over time, but this has become pretty much the industry standard definition. A geographic information system consists of hardware, okay? That ought to be fairly obvious. You need some sort of a computer. Can't run on an abacus. But the computer could be any kind of computer as long as it's got software that'll run on it. All right. So your smartphone, for example, can do GIS, and we will in fact use your smartphone to do GIS later in this semester. But laptops, desktops, this is a dedicated GPS device that has GPS and GIS embedded in it. Lots of different computers, but you need some sort of a computer. You then need some kind of software. The software we are using in this class is called ArcGIS Pro, but as we'll see in a moment, it is not the only kind of software available that does GIS. Just happens to be the industry standard, so that's the one we're using here. You have to have data, specifically spatial data, S-P-A-T-I-A-L, spatial data, data that is tied to a location. If you don't have that, the hardware and software have nothing to work with. All right. This is something that people in the early days of GIS didn't really appreciate. Many of them tried to use GIS to do some sort of a project and only later realized, again, we're talking the late Cretaceous period. Dinosaurs walked the earth, and there was no existing off-the-shelf GIS data. If you were going to do a GIS project, you had to make all the data yourself. All of it, because none of it existed anywhere else, unless you were lucky to stumble in on, like I did at one point, my study area happened to just be where the federal government had just finished doing their own project, and I went to a conference and was listening to this talk, and this lady said, yes, we just finished this project and we have 2.7 gigabytes worth of data that we've completed that's available free of charge to anybody who wants it. Boy, was I up there like a flash to see her. So spatial data is something you have to have in order to be able to make your GIS work. Metadata. Kind of an odd word. Who can tell me what they think metadata means? Any takers? I think he just suggested from his experience, I guess, working with imagery data, right? Camera data. Yeah, that when you're dealing with data from a camera, there's data hidden in each image. Every time you take a photo nowadays with a digital camera, that says all the information about, how big the photo was and where was it taken and all sorts of other things about the format. So that's data about what? More generally, you're talking about specifically, that's information all about the photo, but in general, metadata, if I was applying that word to anything and not just camera data, the definition would be, somebody else had their hand up over here. Somebody know what I'm looking for? Metadata is what? What does the word meta mean?
Well, said it was data about data.
That is exactly right. You win. You win. Yeah. It is data about your data. How many people have used the expression, oh, that's so meta? It's like, yeah, you really probably should know what the definition is before you use it. But the idea, it's kind of self-referential, right? It's data about your data. So metadata is very important to GIS because when you get spatial data, as many of you will, all of you will, as part of your project later this semester, you download it from the internet. It's not always obvious how to interpret it, okay? What if you opened up the data, and say it's data about, well, I don't know, wetlands. And there's a field in there called QR74. What does that mean? Or there's another one called wet type. What does that mean? You don't know unless you have the metadata that explains what are the field names, what do they mean, when was the data collected, how much is it reliable, what uncertainties are there about the data. It's data about the data. So that helps guide you in the use of the data. A relatively recent addition to the definition, I say recent, 10 years, 12 years, is processes. Why would we include this as a definition of a geographic information system? Well, it's because in most uses of GIS, particularly in a enterprise setting, how many people know what I mean when I say like an enterprise? Okay, so when we talk about like computers, if you go and buy a laptop and take it home, you're using it in a home setting, a personal setting. If the university buys 3,700 laptops, puts the same software on all of them, distributes them to classrooms all over the university, and networks them together, that's an enterprise solution. That is a solution for the whole organization. In fact, Canvas that you're using right now, web courses, that's an enterprise solution because it's for everybody across the whole enterprise. Many enterprises have things they do that are routine, that you do every day. Sometimes you do dozens of times a day. How many people have ever had to go to the planning department to get a permit for something that was happening on your house? Anybody ever, or accompany your parents to do that? Nobody has that experience? Okay. What was the thing, if you don't mind me saying? Oh, so she's the one on the other side of the counter. Okay. So people come up to your mom, and there's things that they need to get approvals for, or they need to get a permit, or they need to get, an answer to a question about what can they do with their property. One of the common things that happens in a planning department is a determination of whether your land is in the floodplain. Everybody know what I mean by that? The flood-prone area, the area that's likely to flood every 100 years on average. If your land is inside the 100-year floodplain, you must, by federal law, buy flood insurance. If you're outside the floodplain, ding, 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 you don't have to buy it. Is it a good idea? Maybe, depends, but you're not required. So one of the things that homeowners often do is they'll show up in the planning department and they'll say, I don't know if I need flood insurance. Can you find out? And the lady behind the counter will say, what's your address? And you tell her, and she goes on her keyboard and puts in your address. Behind the scenes, there's a GIS analysis being done. Here is your property. Here is the floodplain. Are you inside or not? No, you are not. And it answers yes or no to her screen. Doesn't even show her a map. It just answers the question. In the floodplain? Yes. Sorry, you have to buy flood insurance. No, you don't. Thank you. And the customer walks away. Now, there's a GIS analysis involved, but the operator didn't have to do the GIS analysis because there was a standardized process. Somebody programmed in, and it does it behind the scenes for her every time she asks that question. There's lots of examples of this. Where I used to work, and I may as well tell you where I worked. It was an engineering firm called HDR, named after three guys who are all dead now. But originally established in 1917, so it's over 100 years old. It's a pretty good firm. Our wetland scientists, for example, had, in fact, all the environmental scientists and planners had a number of things they had to do when they were doing an environmental impact statement. They had to determine, is the proposed project in wetlands? And if so, how many acres of wetlands is it going to affect? And how many floodplain acres is it going to affect? And is it going to affect any endangered threatened species habitat? And is it going to affect any historical sites? You see where we're going with this? There could be dozens of these analyses. By having a script written, a process, you tell the computer, hey, here's all the data over here in this folder, and let me run the process, and I'm going to lunch. See you, computer. I'll be back after lunch to get the answers. I had an experience with, after I'd become the national technical director for GIS at my company, a guy I'd worked with on a project years before got in touch with me and he said, we're out in Texas. We have this problem where we were going to have to look at like 36 different potential roadway alignments for what was called the NAFTA highway through Texas. It went from the Mexican border up to the Oklahoma border, but there were like 36 different alternative ways to do this. You could go this way, you could go that way, you could go this way and then turn left. There was like 3 dozen of them. And he says, I think we're going to need GIS for this. Do you have anybody you can send me? And I said, sure, I can send you my technician, Paul. And he says, okay, send him up. We'll keep him for a week. And then if we like him, he can do the job. We have about 3 months of time budgeted for this activity. I hung up on this guy. I called Paul in. I said, we're sending you to Dallas. You'll be done with this. I'm sending you on Monday. You'll be done with this by Thursday before you fly back. And we talked about it. And he says, oh, yeah, piece of cake. And he did. He went there and he solved the whole problem the other guy had budgeted 3 months for in 1 week. Less than 1 week because he flew back on Friday morning. So that's the power of having standardized scripts and processes. The final component is people. And this was something, again, that early in the development of GIS, the folks that were managing the GIS program often forgot that they needed to invest in training and continuing training for their people. Because if the people aren't adequately trained on how to use the hardware and the software and the data and the metadata and the processes, you got nothing. Or you fall behind. Maybe things are going swimmingly for a little while, but if people aren't kept up to speed with the new versions of the software and all sorts of new technology, they're going to fall behind. So all of those things collectively, we refer to as a geographic information system. They all work together. So they all talk to one another. The hardware runs on the software. The data is visible through the software. There's metadata about the data. Those things are all interconnected. Plus, it makes a nice slide, huh? All right, so let's talk about the functions of GIS. We've talked about what it is. What does it do? And one of the things that, whenever you're like at a cocktail party, which who does that anymore? You're at a picnic, you're at the beach, whatever, you're talking to other people, and they want to know what you do for a living. And if you do what I do for a living, or used to anyway, inevitably you're trying to explain, what does a geographic information system do? And one of the things that people are all familiar with today is Google Maps or Google Earth. All right. So you usually make some sort of analogy that's relates it to one of those products that people are familiar with. But neither of those things is an actual true GIS, because it doesn't do all the things that a true GIS does. One of the things that a true GIS has to do is capture spatial data. It has to have a way for you to actually take new information and get it into the computer. How many of you have added data to Google Maps? Other than typing in and edit like, this store is closed, and they look at that and they go, yeah, we agree, and then they take it off the map. There's not a lot you can do. You can't change the shape of this building, for example, the way it shows up in Google Maps. It doesn't allow you to edit. You have to be able to store the spatial data somewhere. Well, everything does that. Here's the key distinction. You have to have the ability to analyze spatial data. So what do we mean by that? Now, Google Maps does have some limited spatial analysis capability. It has to do what it does. When you ask it, what's the best way to get from here to the nearest Starbucks? It has to find the nearest Starbucks, and then it has to figure out where you are, or you tell it where you are, and then it has to figure out what's the best route, perhaps based on traffic, to get you from here to the Starbucks, right? And then it tells you, turn left, turn right, go straight, and it gets you there. All right, that's called a network analysis or a navigation analysis. But that's pretty much all it knows how to do. It's sort of a one-trick pony. It can find locations, and it can tell you how to drive from point A to point B. That's pretty much it. So if I had a problem that did involve driving from point A to point B, Google Maps couldn't help me. And you're probably thinking to yourself, what other kinds of problems are there? Well, say I wanted to know, let's see, there's thousands of hospitals in the state of Florida, and there's thousands of fire stations in the state of Florida. If a hospital is too far from a fire station, it's at risk of burning down before the firemen get there, right? So I could ask GIS, how many hospitals are more than 3 miles from a fire station. That's a 10-minute operation. And that includes finding the data. All right? Go online, download the data from the internet, do the analysis. 10 minutes later, you know of all the thousands of hospitals in the state, which ones are more than 3 miles from a fire station. And that's routine. That's simple. That's a standard operation. People do that thousands of times a day using GIS. Cannot ask Google Maps to do that. Hasn't got the first clue how to do that. So it is not a true GIS. Google Earth, great tool, great for, well, I'll use it in class. Great tool for exploring the world. It doesn't know how to do this. So it's not a GIS. Doesn't know how to do spatial analysis. All it can do is show you stuff that it already knows. That's all it does. Kind of like the Terminator. You know, it doesn't feel pity or remorse. It just keeps doing what it's doing until it's done. A true GIS has the ability to publish maps. Now, it used to be the only way that we could make maps was to print them out to a plotter or a printer. Then we had the ability to print them to a file, so you could make a PDF or other kind of, like a JPEG or a GIF file or any kind of file, and share the file without having to put it on paper. But you need some way to be able to publish your information in the form of a map. We also have the ability to publish information in the form of charts and tables. Sometimes what people want is not a map. Sometimes what they want is quantitative information. For example, I used the example earlier of, we have a proposed roadway that might impact wetlands, and perhaps we've got two different alternatives, A and B, and I need to know which one of them is more environmentally sound. Well, one way to tell is which one impacts the most wetlands. Alternative A impacts, 37.2 acres of wetlands. Alternative B impacts 6,494 acres of wetlands. Well, I think we're going with alternative A. Okay, so for that, I only need a chart. I don't need to see a map. In fact, a map might be confusing. What I need is a table that says this one impacts very few wetlands and that one impacts way too many wetlands. Finally, it's common today to also publish GIS data on the web. You've probably used GIS-generated maps. You might not even have known about it on the web. We'll explore some, and one of the things you'll learn to do in the advanced class next semester is how to make one of these for yourself. We won't do that this semester, but the 4301 class involves making your own web map. Any questions about anything I've covered so far? All right, so I've got some examples of, I call it GIS in the news. Some of the news is getting to be a little old, but they're good examples, so bear with me. For example, this thing was extremely hot until they shut it down last year. This was the COVID-19 dashboard that was created by the folks at Johns Hopkins University. And they basically put it together because they realized there was nobody else tracking COVID cases worldwide. So they said, well, we think we can do that. And they just volunteered to do it. And they pulled in data from all over the place and created what's known as an ArcGIS dashboard. This is also something you'll learn how to do if you take my research methods in GIS course, GIS4314. But it's got a map. This is a product made by the same folks that make your software we're using here, Esri, E-S-R-I. But it's got a map, and that map has locations that are tied to tables that show up, in these so-called widgets. And you can see the number of cases associated with these different locations, states, countries, cities. And it's got a graph over here, and it's got a tab for different kinds of maps. So you can click on the tabs here and you can get different displays in the center. People were accessing this in cities, counties, the federal government, hospitals. People were using this every day. Hundreds of thousands of people were using this all over the planet. It was very valuable. And then finally, last year, the pandemic was at a point where they said, you know what, we think we can turn off this process. Oh, and here it's actually a little video I capture, so I forgot to trigger it, but you can see how you can zoom in, and you can find information, click on an individual spot and get the cases for just that city, that sort of thing. So I don't know if this link out to it still works. It might no longer work. Here's another COVID-related map. This is a map called the Choropleth map. We'll talk more about that later. Of states according to what percentage of their residents are fully vaccinated. So you had some states like Florida, where the vaccination rate was, actually pretty high. And then you've got other states like Idaho where it's, pretty low, and everything in between. Here's another map showing vaccination rates by county in Florida. So this is more granular. We were looking at the whole state before. Now we're looking at individual counties. And we can see there's some real differences in the vaccination rates within a single state. Here, up in the Panhandle, near the Georgia-Alabama border, this county has really low vaccination rates, let's say like 28%. Whereas down here, Miami-Dade County has really high vaccination rates, 83%. And then you've got everything in between. And you might wonder, what accounts for that? That the availability of the vaccine is pretty much the same everywhere across the state. We don't have any supply problems. So why would that be? Well, one possible explanation was politics, unfortunately. Politics, as you may recall, got embroiled with the whole COVID-19 pandemic and the various means we used from a public health standpoint to combat it. That's really unfortunate, because one of the things you don't want is politics getting involved in something like public health. But you can see where areas that were of one political persuasion seemed to really buy into the vaccine idea, and areas that were of a different political persuasion were not so interested in the vaccine. And here's a case where you can actually take that spatial data and actually begin to work with it in a statistical environment where you can actually graph the relationship between those two factors. And you can see you end up with a pretty good linear relationship where, as a state becomes more Republican, the amount of hesitancy for getting vaccinated increases. People who are less hesitant tend to be more like Democratic voters. So again, an unfortunate consequence of the way that the pandemic and the solutions to it were politicized. We've had a lot of discussion about inflation. Here's a map showing global inflation around the world, and you can see how some places are doing really great. Australia, most of Southeast Asia, the Philippines, Japan, China's doing well, Vietnam, Laos, Cambodia, Malaysia, some individual countries in South America doing pretty well. Interestingly, low inflation in parts of Africa. France, not doing so bad. The Scandinavian countries doing pretty well. Then you've got, at the opposite extreme, places that are doing really poorly. Russia, really, really hugely badly in Venezuela, 500% inflation. That means, like, if you've got $500 on Tuesday, the next day it's worth $1. I mean, that's really terrible. The United States, where we seem to be complaining and moaning a lot about inflation, we were between 5% and 9%, and it's down less than like 3% now. So you can use GIS to look at things like global statistics. Here's an example of using GIS during a storm event. This was during a hurricane, and FPL had this map that was up on their website, and in real time, they would change this map to reflect where the power outages are in the state. So this was tied to their tracking of power outages, and you could go to this map and see, which of your counties, which county has a problem and which ones don't. This is a map that was generated using ArcGIS Pro, which is going to be the software you're using here in class. And the researchers involved took individual point data. So they had temperature data for individual point locations, and they wanted to make a continuous map that would show temperature across the entire continent, not just individual point locations. So if you watch this video, it shows you how they took that data and generated this map. And then once you have something like this, you can use it to track changes in the amount of warming over time. Here's kind of an interesting map and dashboard where they relate the, let me turn off this pen. They relate the ice cover at the North Pole as it grows and shrinks. So they're looking at the polar ice cap over time has been getting smaller. And in fact, we might lose the northern polar ice cap sometime in the next couple of decades. If you watch this whole video, it kind of, some years it's bigger, some years it's smaller, but then you reach a point where every year it just gets smaller and smaller and smaller. It stops getting bigger. Here's kind of an interesting interactive web map that I'm just going to go out to it. I think you'll like this one. That is about what are called geoengineering projects. Anyone know what that term means? Anyone provide me a? Okay. So what are some of the solutions to climate change and greenhouse gas emissions? What are some of the things that we're trying to do in order to get to net zero and stop increasing the amount of carbon dioxide in the atmosphere?
Build more wind farms and electricity farms.
So what kind of farm? Wind farms. Yeah. So we're using more wind power, since that's, obviously not you generating any carbon dioxide. What other kinds of things are we trying to do to reduce greenhouse gas emissions?
Carbon price.
Carbon pricing?
Yeah.
Yeah. So that'd be a way to discourage people from using a fossil fuel for power and try to get them to use a renewable source of power instead. So that's a good one. Essentially putting a price on carbon.
Trying to slow down deforestation because it helps holding carbon.
Okay, there's one. So if that's kind of a holding action, if you've got deforestation going on, that's making the problem worse because you've got fewer photosynthesizing plants that can pull carbon dioxide out of the atmosphere. So that's a good one. So, converting to both wind farms and solar farms for power production, using electric vehicles, which are more efficient than gasoline vehicles for doing the same job. All of those things are ways of reducing our emissions, but a geoengineering project looks at a different solution, and that is, can you actually pull carbon dioxide out of the atmosphere? Are there ways to actually, on a super large scale, reduce the amount of carbon dioxide that's already in the atmosphere? Well, there's projects all around the planet to try to do that. And this web map tracks those. And you can do things like you can filter this and say, I only want to look at the ones that involve, greenhouse gas removal. Well, that'd be those guys. And I'm only interested in the ones that have actually been completed. Well, that'd be those guys. So you could actually look at then each of those and get information about how's that project going. All right. So they're updating this map on a regular basis so that it's constantly keeping track of these projects around the planet. This was really big in the news. This was back in, I think, like 2011. how many people are familiar with this incident where an entire Thai soccer team went into a cave after the game, and this is something they used to do all the time for fun with their coach, and they didn't realize there'd been a big thunderstorm upstream, and so while they were in the cave filled with water, and they were trapped. So all the soccer team kids and their coach were trapped way down in this cave because those floodwaters had filled the exit. How many people are familiar with that? I saw a couple of hands. Okay, number of you. All right. So GIS got involved in this as they were trying to figure out how are we going to rescue these kids from this cave. They needed maps of the cave system, and they needed, for the divers, needed to know how big is the opening. And so these are maps of at different points along the cave system, what's the shape and size of the opening, because they had to figure out, you know, can I get through there with equipment? If I want to bring in extra air tanks or some other kind of equipment, can I actually get it through with me? And if I need to drag kids out of the cave, are we going to be able to do that? There might be openings where that's not possible. You might have to push the kid in front of you in order to get him through the passage. One of the things they looked at was the geology of the rock above the cave to see whether or not is it going to be possible to drill down from the top of the mountain and actually make a rescue borehole down into the cave. Now, they did this successfully in, I want to say Chile, where they had a bunch of miners trapped in a mine, and they actually successfully drilled down to the mine and then were able to extract them one at a time. And that worked in that situation. They determined by looking at these geological maps, it wasn't going to be feasible to do that in enough time, you know, short enough time in Thailand. You'll notice if you look closely at the map down here, that map was generated by Esri Thailand. It was generated by the people who make your software, and they have a local company there, the Esri Thailand branch, and they were volunteering their services to the rescue. All right, so there's GIS in real time. And in fact, GIS gets used in a lot of real-time natural disasters, hurricanes, earthquakes, fires. GIS is all over it when it comes to any of those natural disasters that are being handled in real time. So this is just another case of having an incident where GIS kind of swooped in and came to the rescue. It was only a small part of the overall effort, but an important part. There's a really great movie called 13 Lives. Has anybody else ever seen this? Directed by Ron Howard. My wife and I watched this about a year or so ago. And it's a dramatization. It's not a documentary. It's a dramatization, but it's very accurate to what actually happened, and it's an excellent. So if you are home and you don't know what else to watch on Netflix some weekend, you might want to try this, 13 Lives. As I mentioned a moment ago, wildfires, another important situation for using GIS. Here's a little video capture of using this interactive website to look at fires, getting information about each fire, what its status is it getting bigger, is it getting smaller? You know, how big is it? How far is, for example, that fire from the city of San Diego? So we can actually measure using the measure tool up at the top. There we go. Pull the measure tool and actually say, okay, that fire appears to be, how far is it from San Diego? It looks like it's 27 miles, so probably not a, other than smoke, probably not a big deal. We're in the election season for the presidential national election, as well as all the other Senate and House races. One of the things that's of a lot of concern by political scientists is the extent to which one party or the other, they both do it to some extent, one party or the other has gerrymandered the congressional districts. How many people are familiar with this term? Okay, most of you, yeah. So for those of you who aren't, gerrymandering, it's named after a politician from, I think, the late 19th century named Jerry, where he was involved in helping his legislature in the state he was in create districts that would protect the legislators who were already on the job. In other words, instead of having fair districts where the voters choose their politicians, the politicians were choosing their voters so that they could stay in office. And the districts that he ended up creating looked very peculiar. They looked like salamanders, hence the name. It was a gerrymander. Well, these political scientists are using GIS to see if they can actually detect whether or not gerrymandering appears to be behind the creation of a political congressional district. And for example, there was one in Florida, what was District 3 up here in the North Florida area, and they successfully proved to the court that that was an improperly made district and it was eliminated. It was redrawn. And now there's a new District 3 that is more fairly drawn. In fact, as we'll talk about later in the semester, Florida adopted a constitutional amendment, I think it was in 2010, that requires that congressional districts be fairly drawn to avoid this kind of thing. But it's a constant battle to oftentimes has to go to court to get it enforced. This is something that was literally in the news just this week. I came across this journal article where these like a dozen guys were involved in looking at mapping whether or not there was safe drinking water available in low and middle income countries. And they used a GIS analysis to predict how many people were likely getting unsafe drinking water in these various parts. So they didn't deal with the industrialized countries of the West. They were only looking at the third world countries basically, and Russia, which is effectively kind of a third world nation now. But a pretty decent use of GIS for that analysis. Lastly, this isn't really terribly newsworthy, but I wanted to end on a nice conservation biology note. We're going to be talking about this paper in the advanced class, but this is where this group of wildlife biologists looked at trying to figure out what is the best habitat corridor to protect between this park area and other park areas nearby to help preserve black bears in that part of the state. And so they use GIS for that, and we'll learn how that worked next semester. All right, so from those examples, you should be realizing that GIS is used for a lot of different stuff. Now, a lot of the examples in this class are going to be environmental examples because A, most of you are environmental studies students, and B, I am an environmental planner and scientist, so duh, but GIS is used for lots of other stuff. You know, here's just a short list of some of the things it's used for, and that's, you know, just scratching the surface. In fact, you can use GIS on pretty much any endeavor where location is an issue, where things are located in space, on the planet, on the surface, under the ground. Anytime you've got a problem that involves things located somewhere in space, you can use GIS to help deal with it. And as I already said yesterday or Tuesday, I want to keep emphasizing that GIS is not about mapping. It's about answering questions about the world around us. It isn't just software for making maps. Maps are the byproduct, are the way that we communicate our findings to other people. You know, like these guys. Maps were the way they communicated their results to the people who read their article. That wasn't the end result. They're more interested in trying to figure out how many people are actually getting good drinking water and how many people are having to deal with bad drinking water. That's the problem. The map is the way you communicate that to other people. All right, so I've been doing GIS in one way or another since 1985. That's been a pretty long time. Was that like 40 years? It's changed a lot. The industry has changed a lot. The perception of GIS by people in government and in business has changed a lot. It was a real uphill battle when I first started this to actually get managers to understand how this tool could benefit them. That's really not a problem anymore. Most organizations have really latched on to GIS as a tool because it's gotten easier to use. As computers have gotten better, the performance has gotten better. Back in the late 90s, we were using Sun workstations that ran Unix software, and they were state of the art. They took hours to run something that you could do on this computer in this room that would take minutes now. I mean, the computers have gotten that much better over 20 years. Increased data availability. I mentioned that earlier. You know, when GIS first got started, if you wanted to do a GIS analysis, you had to create all the data first. Now, you live in a world where many government agencies, cities, counties, federal agencies, as part of their mission, they create GIS data to solve their own problems. But then because they're taxpayer supported, they make their data available to the public, usually at no charge. Not always. State of California, for example, under state law there, they can charge for their data. So it makes kind of a hard state to work in if you're a student. But Florida, for example, we have something called the Public Records Act, which essentially forbids cities and counties for charging for their data above what it costs for them to like burn a CD. Okay, so it's really cheap. And most government agencies nowadays, they don't even bother to send you media. They put it on the web and let you download it. And it's like, have at it. They don't even track it. You know, it's like, have at it. There's increased awareness now of the power of GIS. Again, it used to be something that was so peculiar. A lot of people had no idea what it was. Now it's become integrated. It's a well-known technique that people, even in upper management, are aware of. The fact that there's so much data that's now available on the web. So it's not just available to download off a website, but there's interactive maps, like some of the ones I just showed you, has dramatically increased the visibility of GIS. Lastly, GIS has a proven cost-benefit ratio, or another way of saying that is it's got a high return on investment. For every dollar you spend on GIS, you get multiple dollars back in benefit, either in the form of profit, if you're a for-profit agency, or if you're a government agency, in the form of cost savings. There was a community out west, I think it was in Arizona, that used GIS to try to figure out where do we have leaks in our water system. You know, they live in this arid environment where water is, expensive. It's hard to provide fresh water to everybody because they live in the desert. And if there's leaks, that's bad. They're cleaning up the water to drinking water quality standards, pushing it through pipes out to homeowners and businesses. And if it's got breaks in the pipes and it's just, leaking into the desert, they're wasting millions of dollars worth of water. They use GIS to help them track the amounts of inputs and outputs through their water system, and they were able to find leaks that they didn't know they had, and saved millions of dollars in water they no longer had to produce because they weren't losing it in these leaks. All right, so why are we using Esri data, or I'm sorry, Esri software in particular? Well, you can see this is a pretty old chart from 2009, but things haven't changed really that much. It is the dominant product worldwide. So it's got, in this chart, 33% of the, I believe this is the global market, higher in the US. Other products, GeoMedia, 19% at the time. GE had a GIS product. This company, MDA, I don't even know if they still exist, had 9%. Bentley had 9%. Both Bentley and GeoMedia make computer-aided design software that's used by engineers to design things like roads and buildings and water treatment plants. And so oftentimes, the folks that are already used to using their CAD products naturally would migrate to the GIS products made by the same company, and they would integrate pretty well. The the GIS that Bentley has integrates well with its CAD software. Now, Esri does a pretty good job of integrating with all sorts of different products. So it's not as big a deal as it used to be to, stick with the one thing. You can get these two things to talk to each other pretty well. Pitney Bowes makes a product called Map Info that is targeted right at people that do marketing for a living or that do business siting. Like if you want to find where's the best place to put a new Longhorn Steakhouse, they may be using Map Info because it's optimized for that. But if you wanted to determine like how many wetlands are going to be impacted by a new roadway, Map Info is not the thing to use because it's not designed for that. It's very much a business analysis product. Autodesk is again the maker of CAD software. And then finally, Erdas here, that's actually image processing software that's used for managing and processing aerial photography, drone photography, and satellite imagery. But it also does GIS analysis. It does many of the same sorts of things that your Esri product does, but the emphasis is different. It's an image processing product first that happens to do GIS. We'll find out later as the Esri ArcGIS products are GIS products that happen to also do some image processing. And we'll do some image processing in the advanced class next semester. So why are we teaching you to use the Esri family of products and not, for example, something called QGIS, which is a free public domain open source product? Anybody ever heard of QGIS? A couple of people? Okay. I sometimes get this when I post things about this class on LinkedIn. How many people are on LinkedIn? Oh, not bad. Okay. I'll get people who respond to me. It's like, you dodo, why don't you just use QGIS? Because it's, free. And the reason is places that you folks are going to be looking for work after graduation don't use it. All right. What sense would it be to train you? We could train you in all the GIS techniques. QGIS is a great product. It in fact works very well. And I know people that use it on the job because they do work for small nonprofit agencies or they're self-employed. They're like environmental consultants who can't afford the expensive Esri ArcGIS products. But many of you, if not most of you, are going to be looking for jobs like we talked about the other night. You're going to be looking for a job at the city or the county or the federal government, okay, or a consulting firm, all right, or even some of the bigger nonprofits. They all use ArcGIS. So if we trained you in QGIS, you'd be at a distinct disadvantage when you walked into interview. You might not even make it to the interview stage. They might reject your resume right from the beginning. No Esri experience? Goodbye. Okay? That's why we're teaching you this product and not, you can always learn another GIS product. Once you've learned this one, if you wanted to pick up QGIS, if you went someplace that used QGIS, it would take you like 3 days in order to become an expert at it. I hate to tell you how many different word processors I've learned to use over my career. Once you've learned to use one, or spreadsheets, well, let's see, there was the one on the Commodore 64, then there was Lotus 123, and then there was something called Symphony. Finally, there was Excel, and then there's been like 12 versions of that. So once you've learned one, the others are pretty easy to pick up on because it's just a matter of figuring out how does it do what I already know. I know this one does this. How do I find out where this other one does the same thing? So I've mentioned ArcGIS several times. It's actually a family of products. It's a name that covers all the products that this company, ESRI, makes. So it used to be ArcGIS 10.8.2 was what we were using in this class, but that is becoming obsolete. So we're going to be using ArcGIS 331. I'm sorry, ArcGIS Pro 331. This is the new hotness, and this is likely what future employers will be using when you go out looking for jobs. We'll also be using ArcGIS Online. In fact, that's what you used on Tuesday night. That was the product you used the other night. Later this semester, we will be using this tool called ArcGIS Field Maps. Briefly, you'll learn more about this and another tool called Survey 123 if you take my GIS Research Methods class next summer. Here's a poll I did on LinkedIn, and I won't belabor this other than to say about 33% of the people 2 years ago were still using ArcMap, but 66% of them were at one stage or another were moving to ArcGIS Pro. So that's why we're switching you guys. That starting this semester, we're not teaching ArcMap anymore. All right, so let's talk about actual GIS data. All right, so we've got some definitions. We've talked about how GIS is seen in the marketplace and how it's used. Let's start to actually drill into what kinds of data do we need to be using in GIS and how does it all work. To start with, there's two big divisions in the world of GIS. There's what's called vector data and raster data. And this is for many months ago. So we have two kinds here, vector and raster. All right, so vector, what is vector data? Vector is data that consists of either points or lines or polygons. So when you think about it, pretty much everything on the surface of the planet or underneath for that matter can be represented on a map as either a point, a line, or a polygon. Somebody give me an example of something that would be represented as a point.
Well, that's like a specific UCF.
Like an individual school location like UCF is. Yeah, you can represent UCF as a point on a map. All colleges in the state could be shown as points on the map, right? That's a good one. I saw another hand up over here.
I was just gonna say cities.
Cities could be shown as points on a map? Sure. I can't hear. Oil deposits. Those would be kind of area-like things, wouldn't they, when they cover a big area? But an oil rig is in a specific spot, right? So the oil rig could be a point. I'll give you that one. How's that?
A monument, like the.
A monument. Yeah, the Washington Monument is here. The Jefferson Monument is there. That's good. Population distribution. If it's tied to something like a city, yeah. If it's tied to an area like a county, that wouldn't be a point. That'd be something else, right?
Earthquakes?
The location of an earthquake, yeah. It's like, here, there was an earthquake in Fukushima. There at this location, sure.
The location of like data collection from surveys, like if you're doing research.
Yeah, so like when you're doing any kind of survey. So if you're surveying, for example, one of the things that I got involved with, actually multiple times, was surveying railroad crossings. There's over 5,000 railroad crossings in the state of Florida, and I had a team that went out and surveyed all of them. And then later, I helped the state of Minnesota develop a similar railroad crossing inventory for their state. Lines, what would we represent as lines? What kinds of things naturally would seem to be shown on a map as lines? Highways, that's an excellent one that comes to mind right away. Railroads is another good one.
Rivers.
Rivers is good. Rivers was yours as well. I'll give her Rivers because she had her hand up first.
That's fair.
8.6 from the Romanian judge. That's a joke from the Cold War era where the Soviet pact folks always judge the Soviet countries better in the Olympics. Other lines. Well, latitude and longitude would be features on a map to help you locate your location. So you're right, they are lines, but they're more like what we refer to as being part of the base map rather than the data.
Hiking trails.
Hiking trails is a good one. Yeah, that's a good one. Yeah. Animal tracks. Is that what you just said? Yeah, that's a good one. What kind? Yes, yeah, the basically the flight routes that are followed by airplanes, sure. That's becoming less important nowadays with GPS, planes don't have to follow established routes is more, but yeah, that they still have those. You get what's known as a Federal Aviation Administration sectional chart. It has lines on it that represent flight routes. So that's a good one. So what kinds of things would we represent as polygons? So we already see here states and lakes. Okay. What else would you show as a polygon? Congressional districts. Great one. Yeah. Could be. Yeah. Like habitat, land cover, all that, like forested areas. Sure. That's represented as a polygon. Yeah. Yeah, that ties in with what he just said, that basically anything that is like occupies ground as a type of land cover, wetlands, any kind of forest, you would represent as a polygon. Sure. So those are good.
Maybe school zones?
School zones is an excellent one. Yes, because they are a boundary that occupies space, right? What's another boundary that you're familiar with that you use all the time? You might not think about it too much.
Does that make sense? Region.
A region. But there are regional things like we live in the Southeast region. We also live in the East Central Florida region. So yeah, you can define a region as a set of boundaries, like a bunch of counties or a bunch of states. Sure. Is that what you had in mind?
Yeah.
Okay. There was a hand up over here.
State parks.
State parks. Yeah. Any kind of park, state, federal, local, anything like that can be represented as a polygon. Yes, we actually refer to those as building footprints. The land, the shape that the building occupies on the ground, that's a polygon, and we call it its footprint. How about something like zip codes? They cover the entire area. Everybody lives inside of a zip code. Those are polygons, right? So we can represent things as either points, lines, or polygons. Some things are represented as either points or polygons, depending on the scale. You mentioned earlier that we can represent universities as points. But if you zoom in really close, you have to show it as a polygon, right? Because it has a shape. Who said cities earlier as a point? Cities can be points when you're looking at this scale, but if you zoom in, the city occupies an area. You have to show it as a polygon. Lines. We can show a river as a line until you zoom way in. The St. Johns River is a mile wide in places. You have to show it as a polygon. So whether you show something as a line or a polygon or a point or as a polygon depends on the scale. How zoomed in are you? We'll talk more about that later. Yeah. Sorry. That's vector data. So we can do lots and lots and lots of stuff with vector data. Raster data, what's that all about? Raster data is basically imagery. So when you take a picture with your cell phone, that image is a raster. Okay, we'll talk more about the definition of raster in a moment. So anything that involves imagery, satellite imagery, drone imagery, aerial photography. But we also have things like, say, like a digital elevation model, where it's not a picture, but every little square in the data set has an elevation assigned to it, so it represents the elevation across the whole continent. That's a raster. Or something like this. Weather maps, precipitation maps. Those are all done as continuous rasters. It's not points, it's not lines, it's not polygons. It's just each single spot on the map has a certain amount of rainfall, and when you put it all together, it looks like this. Vector and raster data we often see go together like this, that you've got the real world down here that you need to represent in a digital form. You might represent, say, this lake as a polygon, and this stream as a line, and this marshy area as a polygon, and this grassland as a polygon, and this forest as a polygon. So you can see how we took the real world and we converted it to this digital representation. Now, is it perfect? No. We'll talk more about the uncertainties involved in this kind of thing later. But, you can specify in your metadata what scale you did your mapping at, so that people who use it have some idea of how trustworthy is it when I zoom in or I zoom out. Oftentimes, we'll use vector data as the source to create raster data. So you can see here a raster, it looks like a kind of a waffle or like a checkerboard, where it's got a bunch of little squares, all the same size, and each one of them has a different color based on what kind of land use it represents. The green ones represent the marsh, the blue ones represent water, the tan ones represent grassland. So it's not really a polygon, it's an area that happens to have a whole bunch of individual cells, all of which happen to have the same land type next to one another. That's how we represent the world as a raster. Here is a case where we've got a raster on the left, taken from a satellite, and we actually trace things like rivers and roads off of the raster to create the vector representation. That's a process called digitizing, and you'll learn how to do that in about 3 weeks. Rasters, as I mentioned earlier, are a rectangular array of cells. Each cell is given a numeric value, and what that numeric value means is up to you, the human being. It depends on how you are assigning those numbers to mean something. If what they mean is how bright is that spot, that's a photograph, okay? A photograph or a digital image, like the one you take with your smartphone, is just a raster where every pixel, every picture element, every cell in the raster says, I am this bright, I am this bright, I am this bright. Now, if it just says I am dark or bright, that's a black and white photo. If it says I am this bright in red, this bright in green, and this bright in blue, it's a color image. We'll talk more about that later. But if each point in the raster, each cell, each square has a value that stands for how high it is above the ground, well, now you've got an elevation raster. And if each one has a number that represents what kind of land use it is, in this case, is it conifers or Douglas fir or oaks, then you've got a vegetation map or a land cover map. So a raster can have, you can have rasters that have got exactly the same size and shape and number of cells, and what kind of data it represents depends on what do the numbers mean that you're assigning to each square. In contrast, vectors have a structure that relies on points, lines, and polygons. So we can see a point is a single XY location. It has a coordinate where we have an X location, an X coordinate, and a Y coordinate. And at the intersection of that, that's where the point lies. So you can see here, this is a point that lies at 132,105 in the X direction, 360,452 in the Y direction. That represents where that point is. Question? The accuracy of the representation depends a lot on how big those cells are, right? If the cell is really, really huge, it's going to be a really crude map. But if they're really, really tiny, it's going to look really great because you're going to have the cells are so small. But you see this same thing when you're using a photo, like, if you tell it like, oh, that photo is like really big, let me save it as 640 by 480. It looks a lot worse, but you might still be able to read it. Oh, no, let me save it at 3000 by 2400. Oh, it looks fabulous, but the photo is now enormous, right? We'll get into that more when we talk about rasters in more detail, but that's a good point, is the extent to which the raster represents accurately the real world has a lot to do with how big those cells are. So this is something we'll talk a lot more about in the advanced class. We're mostly going to be using vector data in this class. And let me just refer to, with regard to coordinates, you should all be familiar with this idea of the Cartesian coordinate system. Let me just quickly make a quick sketch here. If I have, the x-axis and the y-axis, I can define, here's a location on the x-axis, here's a location on the y-axis, and where those intersect, that's where my point is, okay? So that's called a Cartesian coordinate system after, who's that named after? Anybody? Rene Descartes. Yes, very good. All right, so we're representing points as a single XY location. Lines are a series of XY locations that are connected. So you've got individual, what we call vertices is the plural. Individual ones, a singular is a vertex, plural is vertices. So you got the vertices connected by arcs or lines, and that makes up a line. The ones at the very end are referred to as nodes. You also refer to the ones at intersections as nodes. So you can see this one, we have this line, and this line, and this line all converge at this point. So we call that vertex a node. So these are just, the terminology that we use. And then finally, polygons are a line that closes in on itself. So you start like at this point, and you go around, and you end at the same point where you started, and that forms a polygon. If it doesn't actually connect, like the snake eating its tail, if it's open, even a tiny bit, it's just a circular looking line. It's not a polygon. To be a polygon, it has to actually close. It has to snap to itself at the end. And so there's tools in GIS to actually check for that, because sometimes you have things that look like polygons. You go, oh, wait, that's not. It's actually a line that just didn't quite make it. One of the things that makes GIS particularly powerful is the fact that you can link points, lines, or polygons to tabular data, data that's in a table. That's what makes the data smart. So unlike if I could go to an artist, I used to work with graphics artists at my old job, and they were great. They were wonderful. They were brilliant. And I could tell them, I need a diagram that shows like this road and this, this forest and this lake and they could do that. But their data was dumb. It was like, okay, it looks like a road next to a lake, next to a forest, but the graphics image didn't know that. It just knew, am I green? Am I gray? Am I blue? That's all it knew because it was a picture. GIS is different. It might look fabulous. It might look very attractive, but the key thing is everything in there, every point, every line, every polygon has data in a table that's attached to each feature. Every point, every line, every polygon has a line of data in a table. So you can see this one, this up here, this represents parcels on a cul-de-sac. So here is, the roadway. You probably, some of you maybe have grown up on a cul-de-sac, but it's basically like a dead-end road in a subdivision, right? You've all seen these? Okay. So here's a cul-de-sac, and here's the parcel that's out on the main road, and then here's the one next to it, and the one next to it, and here's one that's, this pie-shaped lot. Great for dogs if you got a big backyard. That's going to be great for your dog. So we've got this pie-shaped lot, and it has associated with it a number. The property appraiser who manages the parcel data for the city or county gives every parcel a unique ID code. This one is 334-1626-004. That's its parcel ID number or parcel so they all either call it the PID or the PIN, the parcel ID number. So this is called the PIN here. So we can link that parcel up with a line in this table. We have this table, and here is the line of data for parcel number 334-1626-004. It's 9,254 square feet. Its address is 347 Cherry Court, and it's single-family residential zoning. Okay, that's great. And it could go on and on and on. Sometimes the people who manage the data don't want the table to be too enormous because, you want to be able to, have it open really fast. And if it's too enormous, it's going to take a long time for the computer to bring it up on your screen. So they might have a table that's only got this much basic information. And that's usually what you need for most routine requests. But then it's like, okay, if I need more information, I can use that parcel ID number to do what's called a relational join. I can join another table up where I connect this table down here, if I can find my cursor, this table down here, it has the same polygon ID number in it as this one. And I can tell it, join those two tables up based on their polygon ID. So now I extend the table and add these additional fields. I now know the owner and what year the property was purchased and what's its current assessed value and what's its tax status. And I can do that with any kind of data. As long as it has that parcel number, I can join it to the main table and I know all that information about that parcel. You can do this with anything. Roads, fire hydrants, wetlands. You will in fact do this with wetlands. When you digitize wetlands 3 weeks from now, you will give every wetland an ID number, and then there'll be a separate table that was created by the biologist who identified the wetland, and it's got all the information about the wetland, and you will use this technique to join the wetland data up with each wetland. So each wetland knows all of its information, and it's smart. Initially, all it knows is, hey, I'm wetland number 37. That's not very smart. But once you've teamed that up with the tabular data, he now knows lots of stuff about himself. Oh, I'm a cypress swamp. And my condition is fair, you know, and all this other stuff. All right, here's what the attribute table looks like in ArcGIS Pro. So here is the interface for ArcGIS Pro. We'll talk more about, you know, what we're looking at here, all the details, but you can see here we have a data layer that consists of counties. And here we have a table where we've got the name of each county right here, the state that it belongs to, some codes that represent the state and county, how big it is in square miles, what's its population per square mile, how many households, how many males, females, and that goes on and on and on. There's about 30 columns of data associated with those counties. So there's a lot of information for each county. There's roughly 3,197 counties in the United States, so it's a lot of data. Here is a list of the functions that are at the top. If you look at this, there's an interface right here, right at the top of this table. There's a bunch of little icons. This is a list of the things you can do, what each of those buttons does. So we're not going to belabor this right now, but I wanted to put this in so you can refer back to this. If you need to know what a particular button does, you can come back to this slide. You might even want to print this slide out so that you have it with you later in the class. So, like I mentioned a moment ago, we can relate data tables to anything, points, lines, or polygons. That requires there be a relational field. In other words, a single column in the database that's in common between the GIS data and whatever table it is you want to join. They have to have something in common. There are some fields that are generated automatically by the GIS. The GIS automatically gives every feature, every line, point, and polygon gets a number assigned to it. That's usually not a good choice to use as the relational field because it's not stable. If you go in and edit the file, like you go in and say, you know, delete a couple of lines or add a couple of lines, it might renumber the entire database. And what was usually previously feature number 1,427 now has some other number. That's bad. You constantly would be having to change your data to try to keep up with it. Instead, what we want to do is use user assigned values, like that parcel ID number. That's assigned by the human being involved. That isn't going to change unless the human being decides to change it. The computer can't change that arbitrarily. You're in charge. If I give a wetland ID number, it stays that wetland ID number unless I change it. Whereas the automated, which polygon is this? What line is this? That the GIS assigns, that could change. All I have to do is make a minor edit and all of them could get renumbered. It's a very unsafe way to, I've seen people try to use the automated polygon ID or line ID number, and it's a real risky thing to do. Just a summary here of some of the other data formats that we might be dealing with. There's some really old data formats known as coverages and shapefiles. We still see a lot of data in shapefile format because it's easy for organizations like cities, counties, and the federal government to store data in that format and make it available on the internet for people to download. It's not a particularly good data format to use. So what we recommend is if you get data in shapefile format, you ought to convert it into what we refer to as a file geodatabases format. Now we'll get into more about the details on that later. I'm just giving you the overview. Don't worry about we'll get into the detail. I'm not going to expect you to understand this from just this one slide. The coverage format is so ancient, ArcGIS Pro won't even open it. Now, if you find data in that format, we could go back to a previous version of the software, ArcMap, and then convert it. You want to try to stay away from that if you can, but sometimes the only way you can get something is in this format, so we still see that show up sometimes, but it's getting to be pretty rare. There's a lot of different raster formats. There's something called the grid. There's a lattice, then there's all sorts of image formats. These are just a few. The GeoTIFF, you've all heard of TIFF files. There's a GeoTIFF that not only is a TIFF file, but it actually knows where it is in space. That makes it a GeoTIFF. Mr. SID and Imagine are image software files used by various software products. We'll learn more about this format next semester, the triangular irregular network. That's this guy right here. That's a tin, and that's used to produce a three-dimensional surface like the one you see behind it. This is the tin that represents that 3D surface. So at this point, I only need you to know that it's a type of data format. We'll get more into what it is and how it works next semester. Like I said a moment ago, we'll be using file geodatabases. It's not really a data format. It's more of a data container or data storage area. And you can have any of these other kinds of things, lines, points, polygons, raster images inside a file geodatabase. There is an enterprise version of that that's called ArcSDE for Arc Spatial Database Engine. That's a really advanced thing. We're not going to even touch that. But you might end up working for a big organization like a county or the federal government where they have their data stored in that kind of database, where they're having to deal with thousands of users. They might have this very advanced enterprise level database. As I mentioned, the coverage is obsolete. There's another format called the personal geodatabase, which is also obsolete. So again, if you run into that, there are ways that we can convert it, but you ought to try to, if you can avoid it, you ought to stay away from it because otherwise it's kind of a pain to work with. All right, so what we're going to do now is actually do some hands-on stuff for about the next 15, 20 minutes. So here's what I want you to do. This is something you need to do on every computer on which you're going to use GIS. So you'll do this tonight on this one. And this is why you don't want to go to a new computer, because then you'll have to do this over again. Okay. But one of the ways in which I think I already mentioned that you can use GIS for this class is we'll have access for you to a remote version of ArcGIS Pro that you get through UCF Apps. So basically, when you log into that, it's kind of like you're running a computer by remote control. You're going to want to do this on that one too, because it's never seen you before. You're going to need to do this stuff on that one. Every computer you sit down at, if you go to the Tech Commons or you go to the lab downstairs, the first thing you're going to want to do is this stuff. Why? If you don't do these settings in Windows Explorer, it just makes Windows Explorer a lot harder to use with GIS data. Okay. So I'm going to demonstrate up here what I want you to do, and then have you do it. Now, we don't have a TA yet, so bear with me. I might have to run around a lot to, if anybody runs into trouble, okay? All right, so here's what we're gonna do. What I want to do is tell you what we're gonna do, and then I'm gonna show you what we're gonna do while you're doing it. And then we'll make sure everybody's caught up before we move to the next thing to do. Is everybody okay with that approach? Anybody not okay with that approach? I'm going to throw you out. Okay, no, okay, good. Everybody's on board. All right. So what we're going to do is there's several things if you open Windows File Explorer. How many people have never opened Windows File Explorer before? Okay, everybody's done that. Fabulous. I've had people that have never even seen it. We're going to open Windows File Explorer, and we're going to set first over here this navigation pane. There's a number of settings over here that we want to turn on, and that makes all the things in the navigation pane turn on. By default, most of them are turned off. So we want all these things to display, so we're going to turn all those things on. Then we're going to go over here, and in the different ways that the data pane shows, we're going to turn on the details. That will show us the date, the type of image, the size of the image, or I'm sorry, the type of data, the size of the data. It's going to turn all those details. Very critical. We're then going to turn on what's called file name extensions. Now, by default, Windows, to look more like a Mac, some years ago, they started turning these off by default. That's great as long as you know what the little icon means, and okay, that's a PowerPoint and that's an Excel, I can tell from the little icon. Many of the files that we're going to be using in GIS have no icon. See this one right here? Has no icon. That's because it is not a file you can double click on and have it open. Can't do that. Windows doesn't know what it is. So the only way to know what it is to have the extension turned on. The extension is this information that shows up after the decimal point. See where it says exercise 01.atbx? This part is the extension. That's turned off by default. We're going to want to turn those on. Otherwise, it's very hard to tell. You might have 7 files all called states, and you can't tell what's the difference between them. Well, the difference is one states.shp, one states dbf, one states shx. There's different extensions, but you can't tell that unless you turn the extensions on. Lastly, we're going to go to this options, and we're going to change some options under here. Okay, so let's start by setting these things all the same, and then we'll click the options and do those. So I'm going to discard that and get out and go ahead and run Windows File Explorer. Now you can start anywhere. It doesn't matter what you display over here. This PC, whatever. Doesn't matter what we have on the right. So let's go to where it says View up at the top. Now, if this menu up here keeps disappearing, that's because it's got this minimize ribbon might be set like that. You want to expand the ribbon so that it shows you that bar with all the tools at the top. Sometimes your version of Windows, it might have a pin where you have to actually tell it to pin that so it doesn't hide. This has an up and down, minimize and collapse or expand. Okay, so everybody have the view tool visible, the view toolbar visible? Okay, great. Let's all go to navigation pane and turn on expand to open folder and show all folders and show libraries. So now when you look at the navigation pane, you should have all those guys turned on. How are we doing? Everybody got that? Great. All right, now let's go over to this middle area, and currently you can see mine set to tiles. Let's change that to details. So now you can see I've got, the type, the size, and depending on where I'm at, it will also show the last time that file was modified. So if I go to where I've actually got some files, for example, like here, you can see the date modified, the type of file, and its size in kilobytes. All right. You don't have anything like that yet. Don't worry about it. Okay, everybody got the details set properly? Now, as you can see, depending as you move around, it might change. Like there, the desktop defaulted to a different display. Just click on it again and change it back to details. All right, let me go back to this folder just to demonstrate the file name extensions. You can see right here with that turned off, I can tell it's a PowerPoint file because of the icon, but it doesn't have an extension. When I click on file name extensions, it now says PPTX. You see that? So you might not have any files yet to look at, but trust me, when you turn on file name extensions, now every file will tell us what type it is using an extension. How are we doing? Everyone got one of those? Okay. Lastly, we want to go over to where it says options and click down the options and go to the change folder and search options. And this box pops up. Click on the view tab in that dialog box. This is, by the way, it's called a dialog box because it's sort of having a discussion with you. You're having a dialogue with the computer, hence the name, dialog box. So there's a few things we want to do in here. Let me go back to the PowerPoint for a moment. All right, so we're going to want to turn on the always show menus. We've already turned off the hide extensions. That should be okay. We also want to do it, I forgot to highlight it, the display the full path in the title bar. We want to do that one. And then we also want to scroll down and tell it, oh, there it is, to show drive letters. Okay, so those are the things we want to set in there. So let's try that. So we want to always show menus. Let's turn that on. That's this one right here. Display the full path in the title bar. Turn that on. We've already turned off the hide extensions. We want to scroll down and it says show drive letters is already turned on mine. So just make sure it's turned on yours. Okay. So are you looking at drive C or D or whatever? Just make sure that's turned on. So tell that okay. All right. So you're going to want to do that every time you sit down at a new machine where you want to use GIS, because otherwise life is harder. It's not impossible, it's just harder. One of the things that's optional is whether or not you want to use the checkboxes. You'll notice like here, if I want to copy this file, I can check it to say, I want that one. Or I could turn that off, you know, and then all I can do is highlight it to say I want to select it. I kind of like having the checkboxes because it's a really sure way to make sure you're talking about that one and not that one. But that's up to you. That's a matter of taste, whether you use the checkboxes or not. All right, everybody got File Explorer good to go? Oh, you guys are doing great. Okay. The next thing we want to do is create a folder where you're going to put all your class data. So we're going to have you go to your documents folder, and then in there we're going to have you create a GIS3043C folder. Now it's very important when you do that, it must have no spaces in the name. Those of you that have Macs, you probably have folders with all sorts of, like, this is my folder for class. Don't do that. GIS has some code in it that dates way back before Windows, and it doesn't understand sometimes spaces in names. So what happens if you have a space in any of the folders that lead to where your data is, when it runs into that space, it explodes. It's not happy. It's not a happy experience. And the error message it gives you will give you no clue as to what the problem was, because it will not say, oh, I encountered an embedded space. No, it'll give you some completely bogus error message. And we have to actually carefully look at the path for your data to see, is there a space in there somewhere? And if we don't notice it, you know, we could be spending hours trying to figure out what's wrong with your software. So what we're going to do here is create that folder. Then we're going to download a couple of things from web courses. We're going to download this file called exercise1.zip. There's also one called esridata.zip. We may as well go ahead and get at the same time. We'll need that later. And we're going to unzip those and put them under your GIS 3043 folder. Okay? So that's the plan. So we're going to go to your documents folder, create this new folder called GIS 3043. We're going to also create a folder called zip data where we can store things that are zipped up. Notice here, we don't have a space. What we have is an underbar. So anytime you want to make a space in a name, you can use the underscore or the underbar, and that kind of visually makes a space, but you'll notice there's no real space there. The software is okay with that. So let's try that. All right, so let's go to your username and the documents folder. Okay, we all there? Everybody got that? All right. Now you can either over here in the view area or over on the right in the navigation pane, either place, you can tell it right mouse click, new folder. Usually it waits for you to name it. Mine didn't. It just kind of created a new folder. So you can click on it and rename it GIS3043C. Enter. All right, no spaces. Now, underneath that folder, again, you can either right click on the left over here and tell it new folder, or you can double click on the folder to get inside of it and right click over here on the right. Either way, you can tell it a new folder and create a folder called zip underscore data. The underscore is above the P. So now if I look over here at the navigation pane, I can see there's a little greater than sign that if I click on it, shows me that there's a folder underneath that folder called zip data. That's why we turned all these things on the navigation pane, so we could kind of maneuver over here. Now you might be tempted, hang on a second, you might be tempted to like, this is all crap. I'm just going to do it the way I'm used to doing it and the way I want to do it. Feel free and fail, okay? Because folder structure is really critical to the way we do things. And if you create a bogus folder structure that makes no sense to me or the TA, we're going to have a really hard time supporting you. There's a reason why we're asking you to do things this way. Bear with me. You'll see later, I've had students tell me, I'm so glad you were insistent about folder management in your class, because now that I'm on the job, I see how critical it is. Or even later in a course, you might realize how critical it is. For now, just bear with me that it's going to be important. So even though you might think, I'll just call it whatever I want. Not a good approach. All right, let's go to web courses. And if we go to the modules, you will see under class 2, there is a exercise1.zip link. If you click on that, it takes you to this page and it says, okay, I can't show you that, but I can let you download exercise1.zip. So click on the download link and it will then download that to your downloads folder. So tell it, yes, go ahead and do that. And up here in the upper right, it says, okay, I've got that. Don't click on the open, click on the folder so you can see it in Windows File Explorer. Okay, so I can now see that exercise1.zip is inside the downloads folder on my PC. How are we doing? Everybody got one of those? All right, hang on a minute. So let's back up while we're here in web courses. Let's just go back to the previous screen. And while we're here, let's go ahead and download this esridata.zip. Same deal. Just click on the download tell it, yeah, go into downloads is fine, tell it to save. It'll do that. We already have a Windows File Explorer open to the downloads folder, and we can just look at it. And when it's finished downloading, this unconfirmed thing will go away. And it tells us, okay, we've got the Esri data.zip. Okay, question? All right. How's everybody doing? We got about, only about 3 minutes. Let's see, I think we can finish doing this one unzip. And then we'll stop there and then we'll pick up where we left off the next time, okay? So you should have a Windows File Explorer over here on the right that has the Esri data and the exercise1.zip. On the left, you should have your focus pointing at the GIS folder. So we can see what's inside the GIS folder is now just that zip data folder. Do we all have one of these on the left and one of these on the right? Everybody got that? So the easiest way to extract something from a zip file is as follows. There's about 14 ways to do this. This is the easiest way. Double click on this file called exercise1zip. That gets you inside the zip file. This is what's inside the zip file. There's another folder called exercise1. Click and hold on that and then drag it and drop it into the GIS folder. Now you can either drop it here in this white area or you can drop it on top of the GIS folder itself. You always want to be able to see where you're going. If you can't see the GIS folder on the left, it's going to be confusing. But drag and drop that exercise1 over here and let go. And what that will do is it's extracting the compressed data from the zip file and it's going to copy it to this GIS folder. All right, you see what happened? Here's exercise1, the folder. Over there, it's compressed inside of another file. The zip file is a way of moving data around and it compresses the data. You can't use it in that compressed format. See, that's inside of a zip file. Over here on the left, though, I now have a folder called exercise1 that's got all this data, including an ArcGIS Pro document that we can launch the next time we're ready to do this. Okay? How do we do it? Everybody get that properly extracted? Okay. All right. Anybody that had trouble with that, just stick around. I'll stick around a few minutes and help you out. But otherwise, this is a good place for us to just kind of call a halt. So go ahead and close out of your machine, log off, and this will be waiting for us when we're ready to play with it next time. Okay? Ooh.